Here we are going to talk about the RDBMS schema design. So as we mentioned earlier, the database management system contains different levels of abstraction. And earlier we talked about the conceptual data modeling, which means that we can design the data model in the conceptual level, which is independent from the implementation details. But however, those conceptual data model needs to be translated into the RDBMS schema in the you can say the logical level, so that the RDBMS can use those logical data model to communicate with the physical level, the information stored on the hard drive. So here we are going to talk about how to translate from the conceptual data model to the RDBMS schema. So here, as we mentioned earlier, these levels of abstraction, and we talk about the conceptual level, which is about the conceptual data modeling, and you could use different different types of diagram to model the conceptual data model. For example, like the ER model that we mentioned earlier, and there's extended ER model, which is called EER, that supports different you can say different ways to represent some certain relationships, and also you could use the UML class diagram to describe the conceptual data model as well. But however, this conceptual data model is, you can say, independent from the implementation details. So we need to translate these conceptual data model to the database schema in the logical level. So here we are going to talk about how to translate it from the conceptual data model to the logical data model, which is the database schema. So when translating a conceptual data model into a database schema, we need to consider a very important trade-off, which is the space-time trade-off. So the meaning of that is the space means if you want to reduce the redundant data in the database, then in this case, you can have the benefit of saving more storage space, or you could have it could be easier for RDBMS to maintain the integrity of the data in the database. So that's the good thing to consider the space. On the other hand, the time means that the database schema can be designed in the way that it has a fast access or fast query to the data. So the reason for that is because if the data is managed in a different way, then you need to probably use some operations to combine the data together. And to be specific, earlier we mentioned that if you want to join the information between multiple tables together, then this join operation is commonly used, and but however, the join operation is the most expensive operation in the RDBMS, or you can say the join operation is the most time-consuming operation in the RDBMS. So in this case, how to avoid join becomes a key to design a faster or to design a more efficient database management. To design a more efficient database. But however, the design for that will compromise some parts of the space. So that is what I said, the space and time trade-off. So let's take a look at some examples to like introduce you these space-time trade-off. So as we mentioned earlier, if you want to have an efficient database, then in this case, you should avoid join operation, because when you are going to join two tables together, then that procedure is very time consuming, because it needs to compare the information between two tables. So in this case, but however, if you want to avoid join operation, then the schema design will become a big table. So which means that it's kind of like all the information has been already like managed in one big table. Like it's kind of like originally the data was separated in multiple tables, and then you use join to join them together in one big table. And so the schema design is kind of like without processing the join operation, then directly the schema gives you the big table without having the join operation, and it gives you the big table. So this is one way to do it. So in this case, that big table, because it doesn't need the join operation, so the runtime process is efficient. So let's take a look at one example. So for example, let's take this start and film as the relationship as one example, and the cast relationship between these two entities. So a big table means that because if we want to avoid the join operation, then in this case, all the information over here can be stored in one big table. So that big table could look like this. So the name of that table we design it as star and underscore and film. So which means that it's the star plus the film information, and we put all everything in this big table. So as you can see, we have the name of the star and gender of the star and birth year for the star, and then we have the title of the film, director of the film, and year of the film. And finally, the relationship also has one attribute, which is the role. That means what's the role that this star like played in this film. So we also have the role attribute over here as well. So as you can see, in terms of the content over here, as you can see, we have Leonardo DiCaprio over here, and as the name of the star, and then he's a male, and also the birth year is 1974, and one of his like signature, one of the most famous film that he played is the Titanic, and the director of that film or of that movie is the James McCarron, and the year is 1997. And in this film, the Leonardo played the Jack Dawson, so that's the role of him. And then, so as you can see, we put the information of these two entities and also these relationships together in one big table. And the second row over here also is Leonardo DiCaprio, and then the male, gender male, and birth year 1974. And then here is another film that he played, he was in, and then that is the new movie recently, which is the Don't Look Up, where played in Netflix. And the director is the Adam McKay, and then the year is 2021. And in that film, in that movie, Leonardo played the Dr. Randall Mindy. So that's the second role or second data over here. The third one is the Jennifer Lawrence, and the fourth one is also Jennifer Lawrence, and of course, gender is female, and also birth year is 1990, and the films are different over here. One is The Hunger Games, and the other one is also Don't Look Up, and so they have different directors and different years and different roles. Katniss Everdeen and also Kate Dibiasky over here. So as you can see, if you want to avoid join, then in this case you will have a very big table combining all the attributes that you should have for those entities and also the relationships between them. So, like I said, because you don't need to process the joint operation in the runtime. But however, as you can see from this table, you may be able to identify the problem of this solution. So the problem over here, as you can see, is the redundancy, or is the redundancy of the data. So as you can see, the Leonardo DiCaprio, he have the male and his gender and also birth year, he actually repeated 2 times over here. But in reality, he will repeat as many movies that he or as many films that he was in, and then this information will repeat again and again and again. So and same goes to the Jennifer Lawrence, and also for the film as well. So as you can see, Leonardo DiCaprio and also Jennifer Lawrence, they both are in the film Don't Look Up. So the title of the film, the director of the film, and also year of the film, it will also repeat it again and again. So that is the redundancy and duplicates that we will have if we choose to design the database schema as a big table. So to be more clear, so if you want to avoid joint operation, then and you choose the big table, of course the advantage is that the query is more efficient. So you have a more efficient query. But however, the problem is that you will use more storage to store the data, because there are a lot of redundancy and duplicates, and that is one of the problem. And the second problem is that if right now you want to change anything from the big table, and then you must need to pay attention to the robustness and completeness of that change. So just for example, if right now, for example, like if Jennifer Lawrence, she married another person, and then and she changed her last name to other last name, then in this case, maybe the whole database needs to be changed. So you need to change this role from Jennifer Lawrence to Jennifer someone, and then but however, instead of just changing this certain tuple, you also need to change all the tuples that has that is represents the Jennifer Lawrence. So if there is one row that you forgot to change, then in this case the consistency and robustness of the database will be compromised. So that's the problem of having the big table. One is storage, and the other one is the you can say robustness and completeness. On the other hand, if you want to avoid redundancy, and also you want to have an easier way to manage the data to provide more robustness and completeness, then in this case, then you will need joins. Then in this case, you will need joins for the queries. So we use the same, you can say, conceptual data model. So the same conceptual data model can be modeled in a different way. So for example, in this way, we can separate each of the entity and also relationship into multiple tables. So in this case, we could have a star table just for the star, and this star table has the name, gender, and birth year. So we have 3 attributes over here, and as you can see, Leonardo DiCaprio, male in 1974, and Jennifer Lawrence, a female, 1990. So the star table only manage those information, and there's no redundancy. Alright, there, as you can see, there's no redundancy in this table. And on the other hand, for the film table, we have the title, we have the director, and we have the year. And we have Titanic, and also Don't Look Up, and also the Hunger Game. Oh, here actually here is a typo. I shouldn't put these. Don't look up over here. So please ignore this row over here. So basically, the film only contain three data or three tuples over here. So the Titanic and Don't Look Up and also the Hunger Games. So they should be only be three records over here. And then for the cast, you can also use a table to represent this cast. And as also you can see, the cast is a relationship. So it also serves a role to link the star table and the film table together. And in the meantime, it has its own attribute, which is the role as well. So as you can see, the cast table is like this. It has the name of the star, and it has the title of the film and the role that they played in this film. As you can see, we have the Leonardo DiCaprio in links to Titanic and play the role Jack Dawson, and Leonardo DiCaprio played in the Don't Look Up as the Dr. Randall Mandy, and Jennifer Lawrence for the Hunger Games, Jennifer Lawrence for the Don't Look Up, for different roles over here. So as you can see, this name and title, they are the foreign keys, or they are the foreign keys. The name of here links to the primary key in the star table, and the title in the cast is the foreign key linked to the title primary key in the film table. So you may argue that in the cast table, we also have some redundancy over here. So for example, we have two Leonardo DiCaprio over here, two Jennifer Lawrence, and two Don't Look Up film title. So yes, of course, there are some redundancy, but however, in reality, like I mentioned before, we won't directly use the content, the attribute of the data content as the primary key. Instead, we will use an ID for the primary key. For example, for the star table, we may have the star ID, and the content for that will be is usually the integer value, the 1, 2, 3, 4, 5. And for the film table, we will have the film ID, also with using the 1, 2, 3 as the ID. So the redundancy over here will be just only those integers. You can say those primary key integers. So instead of like a larger text like showing over here, like the names and titles are shown over here. So the good thing for these like design to have the tables to you can say represent those different entities and also the relationships. The benefit and advantage of doing this is you save space. You save space. There's not much redundancy, and on the other hand, the management of the data becomes easier. Or you can say the robustness and also the completeness of the data management it can be handled much more easier comparing to the big table design. So for example, like I mentioned before, if Jennifer Lawrence marries someone and change the name, then you don't need to change like the name everywhere, and you just need to change the name here, and then everything will and then then for the cast table, you still use the you can say star ID for the linkage, and you just need to change the information in one place, and then everything is done. So there's not much it's not so troublesome to manage to provide a more robust or you can say that it's much easier to provide the robustness of the data in the database. So that those are the two advantages. One is it saves the space, and the second is it's easier to provide the robustness and completeness. And but however, the problem of this design is it requires joins. it requires joins, especially when you need the information across multiple tables. Then in this case, the join operation needs to be performed to join the star film with to join the star with the film, and by using the cast table to join them together by using the foreign keys over here. Okay, so that's the RDBMS schema design, and like I said, when we translate the conceptual data model to RDBMS schema, the space and time trade-off is one very important consideration. And but however, from time to time, but however, this because this is a trade-off, so that means it actually is based on the needs and also the requirements of the application and the suitability of the data itself, to decide whether space is more important for this application or time is more important for this application. So there's no like perfect design for the schema. It needs to follow the requirements of the follow the requirement of the application or follow the nature of the application. So you could have the more suitable RDBMS schema design. So finally, beside the you can say the RDBMS, we have other types of DBMS over here, and just list out for your information. For example, like the document-oriented DBMS. So especially from the in the big data age, the RDBMS sometimes is not efficient enough to manage large amount of data. Then in this case, there's a trend which is called which is called document-oriented DBMS, and sometimes it is also called the NoSQL database. The NoSQL, the official name for that is called not only SQL. Okay. And the other type of the DBMS is called in-memory DBMS. So as we mentioned in the class, if you store the data in the memory, then the access of those data is more efficient. And the graph DBMS is actually managing the data that has a lot of linkage, or you can say the data that is suitable to be managed in the graph DBMS is kind of like the network data. So you have a lot of nodes, and then those nodes have relationships to other nodes, and then this type of form of the data is well easier to be managed in the graph DB or graph database management system. And some lightweight embedded DBMS is also pretty you can say comes in handy. For example, like the SQLite DBMS, and for the mobile phone applications or for embedded devices, if there's a need to manage data in the organized way, then these lightweight embedded DBMS is well can be useful for those cases. And the object-oriented database management system is one of the spatial type of the DBMS, and distributed DBMS is also one of the solution to address the big data storage issue as well. Okay, so if you are interested in knowing more details of those DBMS, please feel free, and you are encouraged to take a look at those different types of DBMS. Okay, so and here are the references that I use in this like unit, and some of the image credits, and that will be it for this unit. So hopefully through this unit you have some basic understanding to the like the general fundamental information to the DBMS, the database management system. So if you have any question, feel free to contact me.